All right, let's go ahead and get started. So we're going to talk about how to represent any continuous functions of power series. And the kind of the lone approach we have to do that right now is to think about geometric series and whether we can manipulate the function that we're given as either a geometric series or kind of what we talked about last time, if we can get to that point through a derivative or through an integral. So this natural log of 1 plus x very much does not resemble a geometric series. But let's think about this. Is natural log of x plus 1 related to some other function? Is it the derivative of something else, or is it the integral of something else that we might be able to get into this form? Do we recognize anything? Do we know what the integral of natural log of 1 plus x is? I think we can find it, but it's a little complex. Do we know what the derivative of natural log of 1 plus x is? What is the derivative of natural log of 1 plus x? 1 over 1 plus x, right? So is 1 over 1 plus x something we can treat like a geometric series? We can change the sign. So instead of representing this as 1 over 1 plus x, we can call it 1 over 1 minus negative x. So if I represent it that way, that should look like our geometric series sum, right? What's the first term of this thing? 1. What's the second term? What's the common ratio of this? Negative x. So what does the second term have to be? Negative x followed by x squared. So it's going to alternate and increment the power of x every time. So this is what this function is equal to. So we start setting this up as a power series. It looks like that. Now, that is not the function we're trying to find a power series for. So how can I get to the one I want to find a power series for? How do I get from 1 over 1 plus x to the natural log of 1 plus x? I take the integral, right? So I'll kind of follow whatever you want to do. Should we integrate this now, or can we generalize this thing and define it using sigma notation? Okay, let's generalize it. So this function, so f prime of x is equal to this infinite sum. So for a geometric series, how do we write that? What's our first term? 1. Common ratio is negative x. So 1's not doing anything. So here's our power series, right? If this is the power series for the derivative of the thing I want, can I now get to, can I integrate this now? So what is f of x? If I integrate negative x to the power of n, what does that give me?
negative x to the 2n over n minus 1. Or n,
I don't think it'll be 2n.
n plus 1.
Right, n plus 1 all over what? N plus 1. And there's one more little thing we have to worry about here. Yeah, because we have an inside function there. I mean, I think when we started the semester, we might have wanted to go really set up u substitution here, because we do have an inner function that's not exactly x. So if we clean that up a little bit, we should get this sum, n equals 0 to infinity, negative 1 over n plus 1 times negative x to the n plus 1. We okay with that? All right, so here's the power series. And now I want to find its radius of convergence. How can we find the radius of convergence? We could do ratio test. I think we can, there's something we can get away with that's a lot simpler. Because one of the things we talked about last time is that if you have a power series, maybe it was longer ago than I thought. So if you have a power series, if you differentiate or if you integrate, the radius of convergence is preserved. So because of that, let's go back to the one we're on. The series we started with, right? The 1 over 1 plus x, that is, 1 over 1 plus x, that is a much simpler thing to think about the radius of convergence on. So for this series, what values of x are going to give me convergence? Or more generally, when does a geometric series converge? When the ratio is between negative 1 and 1, or when the absolute value of that ratio is less than 1? So yes, we could set up the ratio test. It would tell us all the same thing. It would tell us the same thing that we're about to get to. So the absolute value of negative x is less than 1. That's equivalent to the absolute value of x being less than 1. So if you're asked about the radius of convergence, remember the derivative, taking a derivative or taking an integral does not change the radius. So if there's something simpler you can look at, then by all means do that. Go ahead. Yeah. Dealt with the what? Not with the sigma notation, but with the fact that the inner function there is, something different from x. So if we set this up, so let's take an integral of this using u substitution. So I have negative x to the power of n. So I would say that u is equal to negative x, which means that du would be equal to negative dx. So if I set it up that way, then my integral becomes what? It becomes the integral of u to the n times negative du, right? So I'm going to go ahead and pull that negative out of the integral. What's the integral of u to the n with respect to u? Right. And we're carrying the negative sign. Now I'm going to resubstitute. So what is u? That is negative x.
So that should be equivalent. Yeah, it's identical to what we have. But essentially the derivative of the inside function, think about it the way you would do chain rule. If you're going to take a derivative, you would end up multiplying by the derivative of that inside function. Here we divide by it because we're going in the inverse direction. Go ahead.
So when we deal with problems like these, can you have like a choice on whether to get its integral or its derivative?
Well, depends on what you mean by choice. Like here, I don't think we had a choice. It's going to depend on the case. I don't think the integral of natural log of 1 plus x would have. I mean, you could find it. I don't think it's going to help you get what you need. So we've kind of, with different examples, we've gone both directions here. So the one we ended on last time, I wanted to get a power series for 1 over 1 minus x squared. And we did that through the derivative of 1 over 1 minus x, right? So in that case, we found the power series that goes with 1 over 1 minus x, and then we took a derivative of that. Sound familiar? Okay, so depending on the case, depending on the function that you're actually interested in, that'll more or less dictate which way you want to go. Do you need a derivative? Do you need an integral? So, same kind of story. I'm probably going to need a derivative or an integral to put this into a form where I can use all my geometric series tools. So what do you think? Derivative or integral? What do we know about the inverse tangent or the arctangent of x?
Isn't its derivative 1 over 1 plus x squared?
Does that sound familiar? Okay, so if we believe this, first we'll decide if it's true, and then we'll decide if it's helpful. So the derivative of the inverse tangent of x is 1 over 1 plus x squared. Okay, so do we remember that? Do we believe it's true? Okay, now is it useful for the thing I'm asking? Okay, how so?
We can get the signs.
You can change the signs on what? Okay, so Saul wants to change 1 over 1 plus x squared to 1 over 1 minus negative x squared, which is true. So what do we do with that? What does that allow us to re-express?
You know, the first term of the common ratio.
So yeah, we know the first term of the common ratio of a geometric series. What is the first term? How do you know the first term is 1?
The numerators.
The what?
The numerators.
The numerator is 1. Good. What's the common ratio? Negative x squared. So multiplying that by 1 should give you the second term. Then if we populate a few more terms, we okay with this sum? Okay. So we want to find the power series representation of this thing. Can we do that now? So the last example we just did, first we generalized the power series, then we integrated it. Should we go the opposite direction now? Let's integrate these terms and then generalize it after that. So let's start integrating stuff. If I integrate these terms, what happens? So 1 minus x squared plus x to the 4th minus x to the 6th. I'll catch up to you if you want to start shouting out what some of these antiderivatives are. What's the antiderivative of 1? X followed by negative x to the third over 3. Good. What else? Okay. Are we seeing patterns emerge? Okay. So now we've written out 5 terms in this power. So this is the power series we actually care about, right? This is the one I asked you about. The one above it was a means to an end. This is the one we want. So now can we generalize this power series? One other thing I want to point out is this series up here geometric. Okay, that was geometric. That was the only reason we were able to kind of make a lot of the equalities that we made. Is this thing that we actually care about geometric? What's the ratio of the first 2 terms? Negative x squared over 3. Does that ratio join the next 2 terms? No. So we started with a geometric series. But now we're moving on to something that doesn't fit that mold anymore. But can we still generalize it? So what patterns do we see here? And we can really, if it makes it easier, we can deal with them one at a time. So as we go from one term to the next in our series of interest here, what kinds of things are happening? What kinds of trends do you see?
The numerator is multiplied by negative x squared.
The numerator is multiplied by negative x squared. That's consistent from term to term, right? Any idea how to represent that in my sigma notation?
Negative x squared raised to the n.
Negative x squared raised to the n. So before we populate any other part of this thing, let's think about what that's going to do. When n is equal to 0, what's this thing going to be equal to? It'll just be 1, right? So you're not going to have an exponent. When n equals 2, this will be x squared, right? Or it'll have a power of 2. So we're a little bit off, but I think we can make a repair. I think we can make an adjustment. Negative x to the n plus 2. When n is 0, that's going to be squared, right? Okay, so let me drop it by 1. Does that help? When n is 0, I get negative x. I'm just looking at exponents right now, though, right? We can handle the rest of this piece by piece. When n is 1, I think this will be x squared. When n is 2, that'll be x cubed. So the way we have it written, we're counting, basically we're incrementing our exponents by 1, right? So I think we still need to adjust.
Are we able to do what we did before, the negative x squared to the n, and then just multiply that term by x?
Say that again. I'm not sure I followed.
Like have x and then times negative x squared to the n.
X times negative x squared to the n. Okay. Does this make sense? When n is 0, I should get positive x, right? Do we agree with that? When n is 1, I should get negative x cubed. When n is 2, I should get positive x to the 5th. Okay, so I think we have the alternation and we have the powers incrementing in the way we want. One last thing we have to take care of, and that's what? Denominator. What's the denominator? 2n plus 1. Do we agree with that? Should we verify? When n is 0, what's the denominator? 1. When n is 1, what's the denominator? So it's going to count. Basically, you're going to get the odd numbers. Do we agree with that? Okay, I feel good about this. So I have no preference really. We've kind of done it both ways, where first you generalize the series that absolutely is geometric, and then you integrate or take a derivative. I think you have to do those two things. I don't think it matters in which order you do them, whatever makes more sense to you. So that's the series that I asked you for. Can I find its radius of convergence? So just like last time, the ratio test absolutely will do it. Can we get around that? Is there something easier, something more straightforward we can look at? We can look at the geometric series, right? We can look at 1 over 1 plus x squared. So this thing here, how can I determine where this series, like for what values at x this series converges? What's going to tell us that?
If R is between -1.
If r is between -1 and 1. And in our case, r is what? Not exactly x squared, negative x squared. But is it okay with you if I say that this is equivalent to this? So I think our radius of convergence is again 1. So that's the radius of convergence of 1 over 1 plus x squared. But can I say that's the radius of convergence for arctangent of x? Is that a fair assumption to make? Yep. So that's a theorem we've talked about. If you have a series and you know its radius of convergence, then taking the derivative or taking the integral does not, it preserves that radius. How are we doing? Okay. Last thing we'll do from this section, I want to integrate this function here, which I don't believe is possible using the things that using the integration techniques that we've talked about, like in the first half of the semester. So is there some other way I can think about 1 over 1 plus x to the 7th power? Sorry, what's that? Let's try that. Okay, if we make u equals 1 plus x to the 7th, then what's a consequence of that definition? 7x. Okay. Can we go forward with that? So that's why I think the things that we've talked about in the first half of the semester are I don't think they're going to get us home here, because we can definitely define u that way, but then we're not going to get the corresponding du that's going to help us compute that integral. So think about this in terms of power series. You got an idea?
We let 1 over 1 plus x to the 7th equal f of x, and then find the series for that, and then integrate it back.
So let's see what that does. So you would like to represent this as a power series. Can we do that? More importantly, how is that going to look? How is that going to work?
Would be like negative x to the seventh to the end.
How'd you get there?
I first turned it into 1 over 1 minus negative x to the seventh,
Okay,
and then I just did the first term ratio to the ends.
okay, so you are treating this as a geometric series now, which I suspect you were assuming, but I wanted to make you say it out loud. So we have not 1 over. First term over 1 minus r. So we see that this function can be manipulated to look like the sum of a geometric series, which that means now we can write this thing that's not a polynomial as an infinitely long polynomial. So what's the first term of this? 1, second term? Negative x to the 7th, because what's the common ratio? X to the 7th, so let's populate a few terms. And then I'll actually give you a choice this time. So now do you want to generalize this first, or do you want to integrate all these terms and then generalize that? I got 1 vote for generalize first. Okay. Sounds good. So let's do that. This series is equal to, let's condense all these terms. What's that going to look like?
Negative x to the 7 is the n power.
Negative x to the 7. Like that?
Yeah.
Okay. Do we agree with that? Yeah, n equals 0, that should be 1. N equals 1 should be next to this. Yep, I like it. So this right here is the function I gave you, right? So we replace the thing that we decided would be hard to integrate with something that we hope is easier to integrate. Is that true? Is this thing here easier to integrate? With respect to what?
Yeah.
Yes. What is that antiderivative if we know it?
Basis of n plus 1 over n plus 1 minus 1 over negative 7 x to the power.
I'm sorry, I lost you. So over what? Okay. We share about this. I think we can make this a little simpler, and I think we're getting hung up on. I think the parentheses are maybe doing us more harm than good. So we might end up there, but let me encourage you to do this. Is it okay if okay with you all if I break this up into a couple of parts? So we know we alternate, right? Can I rewrite this way? X to the 7th to the n. Is that okay? If that's okay, can I then say this? So negative 1 to the n times x to the 7n. Is that okay? So now let's integrate this. What's that going to look like?
Negative on the end.
The -1 to the n stays. How come? It's a constant. Yeah, so it doesn't vary with x. So I can treat it like a constant. What else?
The numerator x to the 7n plus 1
X to the 7n plus 1
over 7n plus 1.
over 7n plus 1. How are we doing? I see some skeptical looks. Ask me all the questions.
And next to the -1 to the n.
I say no. But let's talk about it. Why am I saying no? And do you agree with me? Here's what I think you just told me. Here's the logic I think you just used. What's the integral of 5x to the, let's use something different. What's the integral of 5x cubed?
Or
So I think that would be 5 over 4 x to the 4th. But it sounds like you wanted to attach an x to the 5.
I think I was looking at like 2 separate parts.
Oh no, they're
Yeah.
basically it's weird to think of -1 to the n as a constant because it's going to alternate. We know it's going to have some kind of changing behavior. But one thing to address that, this integral, all the integrals we've talked about deal with exactly one variable. And what's that variable for this integral? That's x, right? So anything that doesn't vary with x, we can treat as a constant. Questions here? Go ahead.
So when you integrate the series, the sigma notation just falls.
No, it shouldn't. Thank you. That is a huge miss. Thank you for catching that. No, the sigma notation absolutely does not fall off. Because what is the sigma notation doing? It is, I mean, if I look back at this thing here, when am I going to be done writing terms? Yeah, never, right? So the sigma notation allows me to condense an infinite number of things and generalize them. Good catch. What else? All right, so that's what I have for you for this section here. So basically in this section, you know, we were able to do a lot with it, but our only real weapon was talking about functions that we could somehow bring back to a geometric series. So let's get a little more sophisticated so we don't have to rely on those things. So the thing we're going to talk about for the rest of this chapter are essentially Taylor series, Taylor and Maclaurin series. One is a very specific version of the other, but they're really substantially the same thing. So I have a power series. So very generic. I have a power series whose exponents, you know, increment by 1 with each term. I have a list of some constant coefficients. Do I know what values of x this thing has to converge for? We can either redevelop it or if you remember us doing this from a couple days ago, we can talk about that. In fact, maybe let's not do that. Let's redevelop it. How can I find out for what values of x this thing converges on? Ratio test will get us there. So I'm still kind of borrowing geometric series logic because I want to know what happens to the ratio of adjacent terms as we let n get really big. But let's take a look. C of n plus 1 times x to the n. No, x to the n plus 1 over C of n times x to the n. As usual, I forgot to carry the limit operator. All right, does anything in here simplify?
And yeah.
Okay, so I don't know anything about these coefficients. So I can't really assume anything here, but I know that this is true. Yeah, the absolute value of x to the n plus 1 over x to the n. All you're left with is x, absolute value of x. And I want to know where this thing converges. So what am I doing with this expression? What do I want to be true about it? I want it to be less than 1. Can I say anything yet?
I believe. Maybe a positive, but also absolutely.
Yeah, you're right. But remember, we're trying to answer a question about x. So I think you're answering the question exactly how I asked it. But maybe I want to reframe your answer. So yeah, I'm going to need this ratio here to be strictly less than 1. And I think this is equivalent to what you're saying, if I'm following you correctly. Is that the absolute value of x has to be less than this absolute value. So the interval or the radius or the values where x converges is going to depend on whatever my coefficients are. So generally we have a much better idea of how those coefficients behave than just pulling them from this list of CNs. But typically this is what the condition we put on the absolute value of x.
Should the C n plus 1 be on top?
No. You see why. So basically,
Oh wait, no, I see that.
so yeah, I divided that over. So I had more bullets here and should have thought about that. So can I hide my ink? So here's the rationale behind what we're doing with Taylor's series. We want a function which might not be a polynomial. In fact, the power. We want the function and the power series representation of it to completely agree. So that's kind of that's an intentionally vague term. What does it mean for two things to completely agree? Why is that not working? Okay, so the rationale behind basically, I want them to completely agree, but we have to be very clear about what that means. Why are you not talking to me? Okay, I'll try to do this without marking. But let's say we have some function f of x. I don't really know what it looks like. I don't know how it's defined, but I know that I want to represent this as a power series, which is basically what section 6 was all about. We had kind of one approach that we got a lot of mileage out of, but now we're going to try to expand our tools even further. So what we just said about this thing converging is this, we have the absolute value of X is less than. You know, whatever the ratio of the coefficients are. As n gets really big. But that's pretty general. So. We have seen cases where. Actually, let me ask it this way. When we talk about a power series, there are 3 possible scenarios for convergence. Do you remember what they are? So, like, if I ask you for what values of X does the series converge, your answer can be one of 3 things.
Diverge, converge conditionally, and converge escalating.
So that is, so in power series, we can say a little more, right? Because in a power series like this, so these functions, these series are built, you know, by kind of how n varies, but really this is a function in X. So when we ask what values of X does a power series converge? So in pretty much our last 4 or 5 examples in that last section I asked you about, we found the power series and we asked, or we answered, I think the same question for all of them. Got an idea?
Is it like diverge and then in a range and then all real numbers?
Very, very close. So two of those possible scenarios are we have a radius of convergence where there's some finitely long interval where your series converges inside that, your series diverges outside that, and then the boundaries are, you know, ambiguous. You got to figure that out. Then there's the scenario where it converges absolutely everywhere. And then you said it diverges, but these power series never diverge everywhere. The most narrow way they can converge is at whatever like the center value is. So in this case, I believe this series is going to converge at x equals 0, no matter what. Because of x equals 0, what's true about that series? Or let's go back kind of underneath that a little bit. If x is equal to 0, what can I say about the sequence that builds that series up? It not only converges to 0, but what does the sequence look like? It only has zeros in it, right? So that's what we say, these power series, and maybe it's not clear what I mean when I say center point, so for now we'll just say 0. But I think at 0, this thing has to converge, right? So that is one way, I think, that this completely agrees. F of 0 has to be equal to 0, right? Or do I want to say that specifically? I'll say this, f of 0 has to be equal to C0. We agree that the first term in here is going to be, so I think this will be helpful. Let's write out the first few terms as a general thing. What's the first term of this? C0, right? C0. What's the second term? Not just C1 though, right? C1x plus C2x. Right. So basically I'm pulling from a list of coefficients. I'm incrementing the power of x by 1 each time. We okay with that? Okay. So let me ask this now. So is it okay for me to say that 2 functions are equal? Like, is this enough? F of 0 equals g of 0. Does that mean that f of x equals g of x? That's really irresponsible to say, right? Mm-hmm. So when I say these functions completely agree, it's not nearly enough for me to say that they agree at a point, right? So let's go a little deeper. Maybe they have this point in common, but maybe they're tangent to each other.
So that means they have to share the same derivative, right? What is f prime of 0 here? We figure that out. What's the derivative of this thing gonna look like? What's the derivative of C naught?
0.
Okay. So that vanishes. What's the derivative of this?
C1.
C1. This one is
2C2.
2C2x plus 3C3 x squared plus 4C4 x to the third. Okay. So then what's the derivative at 0? Knowing that now this is the derivative. Not 0. So basically, if I plug in 0 for all the x's here, a lot of stuff is going to get annihilated, but what's going to remain? C1. So, is that complete? Can I say two functions totally agree if these two conditions are true? They share a point and they share a slope at that point. Is that enough to say that these functions are equal? I hear a vote for yes. Anybody else? This meet both of these conditions. I think it does, right? So I think at this point, they both share this point. I think the slopes are 0 on both curves. Is that fair? So this is not complete agreement. Would I get complete agreement if I did one more derivative, one more order?
Yeah.
That would be enough. Or what I would need more, right? So this is basically the way a Taylor series is built. I'm taking a function that has derivative whose derivatives I can find. And I need to build a new function that agrees with this function completely. So now we can talk about what that means to agree completely. I want them to share that point in common. I want them to share the first derivative in common. I want them to share all derivatives in common. So what does that look like? We took a derivative, the first derivative, right? So this is f prime. What does f double prime look like? So this is the last, so this is the first non-zero term, right? 2C2. What's this one? 6C3x plus 12C4x squared, right? So my second derivative here is 2C2, right? Yeah. So I'm gonna have to stop soon, but we have a question about the way this, the logic here. I'm trying to take a generic function and try to build up a polynomial. The function I'm trying to deal with might not be a polynomial, but I would like to treat it like a polynomial because those are a lot easier to predict and deal with. So are we okay with the logic first as well? Go ahead.
When do you know it's equal to f that's equals to g of x? Like,
This is basically how
once you do like how many derivatives?
all of them. Which is that possible though? So there is no last derivative. So basically that's what, and keep in mind that when we set up series, they are infinitely long. I just have to stop writing at some point. So I want to set up a series where they have this point in common. They have the same slope of the tangent line in common. Their concavity is doing the same thing. I don't know, we can talk about what this derivative is. But actually the word is jerk. Where did it go? But obviously all the derivatives have to agree. So I can build up those things using Taylor series. So we'll talk about that more specifically next time. But
all this lead up because I don't want you to think that they fall out of nowhere. I want you to see where they come from. If you have questions, come talk to me. I'll be around for a few minutes. Otherwise, have a good weekend. I'll see you Monday. What's
So
up?
I had a quick, I know I emailed you yesterday about this.
Yeah, did you see my response?
I did.
Okay.
Yeah, I got this number 2 made sense to me. But this one, I'm like, I know in an example, we kind of treated the first term like when you do ratio tests, it just
Yeah.
comes out. But I was trying to figure out how, like, if you square this function, like this power series,
Mhm.
how it affects its radius of convergence.
So, and maybe it'll be more clear for me to say this way because of the way we